It's a very small chapter. We can easily cover this today. S block. So basically, first of all, we are going to write all the elements from S block. It has two groups: alkali metals, the first group, and alkaline earth metal, the second group. Is that clear?
Yes, sir.
Okay. So I'm going to write S block has two groups. The first one is group 1, and that is basically alkali metals. And the second one is group 2, that is known as alkaline earth metals. Alkaline earth metal. Now, how many elements and which elements are present in group 1? So basically, this is lithium, sodium, potassium, rubidium, and cesium. There will be francium too, but francium is basically radioactive element, so we won't study about francium. In the same way, group 2 has element beryllium, magnesium, calcium, strontium, barium, and then radium. Radium is again radioactive element. Now going for the configuration, we can write helium 2s1. Here it will be neon 3s1. Potassium will be argon 4s1. In the same way, rubidium will be krypton 5s1. And then cesium will be xenon 6s1. And in the same way, francium will be radon 7s1. In the same way, we can write the electronic configuration of beryllium. That will be helium 2s2, magnesium, neon 3s2, and then again calcium, argon 4s2, and then strontium, krypton 5s2, and barium, xenon 6s2, and radon, that is the radium, basically radon 7s2. This number basically represents period. Lithium is from second period. What about rubidium? Fifth period. What about cesium? Sixth period. What about strontium? Fifth period. So basically, in electronic configuration, the highest principal quantum number is will give the period of this any element. Is that clear?
Yes, sir.
Okay, just write it and let me know if you are finished with this. It's a very easy chapter. Nara, do you have any doubt in this?
Done, sir.
Nara, are you done? Okay. Very good. Now the next topic is basically hydration enthalpy. First, I'm going to write its definition. Please write with me, and then I will explain it. Hydration enthalpy. What is hydration enthalpy? So basically, the amount of energy released during the interaction of ion with water, since water H2O is polar, is called hydration enthalpy. That I am going to denote it by He. So what is hydration enthalpy? Just suppose if you are going to put NaCl into water, that it will be dissociated into ion Na plus, it is in ionic form, and you already know that H2O is polar in nature. That means oxygen will withdraw electron of hydrogen, so it will be negatively from both sides of hydrogen, and it will be delta positive and delta positive. Now this is negative, this is positive. There will be force of attraction due to which energy will be released, and that energy is called hydration enthalpy. Is that clear, Krishna?
Yes, sir.
So basically, do we compare how do we compare hydration enthalpy? Which element will have more hydration enthalpy, and which element or ions will have less hydration enthalpy? So basically, hydration enthalpy directly proportional to magnitude of charge. Magnitude of charge. You know that if we increase the charge, the force of attraction will be greater, and force of attraction is directly proportional to released of amount of energy released. So if there will be more attraction, that means more stability, that means amount of energy will be larger. So the first point to compare hydration enthalpy directly proportional to magnitude of charge, and the second is basically hydration enthalpy inversely proportional to size of ion. If ion is smaller in size, it can attract with a greater force as compared to the larger ions. Is that clear?
Yes, sir.
So if you are going to see trend in hydration enthalpy, if I'm going to give you a question like Li plus, Na plus, K plus, Rb plus, Cs plus, this is all cation, and I'm going to ask you which one will arrange these ions in decreasing order of hydration enthalpy. So you are going for charge first, and you can see all the ions have same charge, so we will go for size, and you know that which ions will have a smaller size, Li plus.
Yes, sir.
So it will be like this. The smaller the ions, more will be the hydration enthalpy. In the same way, if you are going for the second group, Be plus 2, Mg plus 2, Ca plus 2, Sr plus 2, and then barium plus 2, that is Ba plus 2. So the answer will be like this. Is that clear?
Yes, sir.
So now, if I am going to compare Li plus with B plus 2, can you tell me which one will have larger hydration enthalpy? Krishna?
Sir, I think it's lithium, sir.
What?
Li, sir. Li plus, I think.
Li plus 2. What I wrote here is hydration enthalpy directly proportional to magnitude of charge. If the charge will greater, the force of attraction will be greater or lesser?
It will be greater, sir.
It will be greater. That means the bond will be strong, and if there will be a strong bond, the amount of energy released will be larger or lesser? Larger
Larger,
or
sir.
small? Larger. That means B plus 2 will have more hydration enthalpy than Li plus 2. Li plus.
Sir, but the size is greater, right?
Size is greater. Which one has a greater size? Do you know when we move from left to right, size decreases?
Oh, yes, sir. I got
Lithium
mistake.
beryllium is smaller than Li lithium, and again the ions which have greater positive charge is smaller in size. Always remember this. If I'm going to ask you about Na plus, Mg plus 2, and then Al plus 3, which one will have a smaller size? Aluminium plus 3. So from both the case, or from both the from both the points from here, you can see B plus 2 is a smaller, and if it is a smaller, hydration enthalpy will be larger. B plus 2 has more charge than Li plus. That's why its hydration enthalpy is greater than Li plus.
Yes, sir.
Okay, please write it. Are you done with this?
Done, sir.
Okay. Nara? Now, I'm going to write a point about this hydration enthalpy. Very good, Nara. Of alkaline earth metal, AEM stand for alkaline earth metal, greater than hydration enthalpy of alkali metal. Why it is so? Because hydration enthalpy of alkaline earth metal, the ions of alkaline earth metal will have greater charge as well as a smaller size. That's why. So I'm going to write a good point about it. It is due to more charge density and a smaller size. And a smaller size. Due to a smaller size of Li plus, this is another point. Note, you can write it in note. Due to a smaller size of Li plus, it has greater extent of hydration. We are talking about lithium in its group. This note is about lithium in its group. Greater extent of hydration. Therefore, lithium salts are mostly hydrated. What does it mean? I'll explain it. Please write with me. Mostly hydrated and exist as LiCl.2H2. From alkali metals, only lithium exists as hydrated in this form. No other elements from first group, that is alkali metals, exist in this form because lithium is highly hydrated. Is that clear?
Yes, sir.
Second group is also hydrated because it has more hydration enthalpy. So LiCl.2H2O I can write. In the same way, magnesium exists, MgCl2.8H2O. In the same way, calcium exists, CaCl2.6H2. Down the group, basically hydration decreases because size increases. Because of size increases, SrCl2.6H2O, BaCl2.2H2O. I'm going to write from here, top to bottom, hydration enthalpy decreases. I didn't talk about beryllium. I will talk about it at last. Done, Krishna?
Yes, sir. Done.
Very good. Now, order of mobility in aqueous solution. In aqueous solution. If I'm going to give you a question, Li plus aqueous, Na plus aqueous, write with me. Then K plus aqueous, then Rb plus aqueous, then cesium plus aqueous. Again, Be plus 2 aqueous. This is for second group. We are taking both together. And then magnesium plus 2 aqueous. And then calcium plus 2 aqueous. Then strontium plus 2 aqueous. And then barium plus 2 aqueous. Can you arrange these two questions in increasing or decreasing order of ionic mobility in aqueous solution. Do you know ionic mobility or mobility? What is the mobility? What is mobility?
Yes, sir. It increases with increase of reactivity, right?
Basically, mobility, that means mobile. That means movement.
Yes, sir.
Movement. So basically, in the first group, alkali metal, which one will move faster or which one will move slower?
So cesium will be faster than
Faster, because
radium.
it has very less hydration enthalpy. That means basically, cesium. I'm going to explain this. Li plus, nearby Li plus will have lots of water that Li plus will hold, and since it has lots of water, its mass will increase and it will probably greater mass. That's why it will move with slow speed. So in this, we will arrange in this category. Decreasing, this is increasing order, and in the same way, like this. You can see cesium has very less hydration enthalpy. That means basically cesium is interacting with very less water. Okay, the bond between cesium and water is very less, and the bond between Li plus and H2O is very larger. It will have a lot of water molecules around it. That's why its mass increases and it will move with slower speed. Is that clear, Krishna?
Yes, sir.
Okay, thank you. There will be another question about size. It is of two types. Like I'm going to give you two questions. Order of size. Order of size. One is normal, like Li plus, Na plus, and then K plus, and then rubidium plus, and then cesium plus. And the another is same atom, same ion, but in aqueous solution. Can you arrange it in increasing or decreasing order of their size? There are two questions. Can you do this?
Yes, sir.
Okay, please do it. Are you done with the ionic mobility in aqueous solution?
Yes, sir.
Okay, let me have a question first, and then if I will ask, what about the mobility of this without aqueous solution? What will be the mobility without aqueous solution? That means uh, uh, you are not going to keep this Li plus or Na plus or K plus, Rb plus or Cs plus in water. Without water, what will be the mobility? The one with a smaller size or the one with, we can say, a smaller mass. So the mobility will be this type or not?
So for what's the condition, sir?
What's the
So condition, sir. I didn't get the condition.
conditions? This aqueous represents that this Li plus is in water. Is that clear?
Yes, sir.
It is, if it is present in water, that means it is interacting with water. That means we know that Li plus will, if it is present in water, it will have more hydration enthalpy. Li plus will be surrounded by a lot of waters. That's why
Yes, sir.
its mass increases in this case, and it will have slower mobility. Is that clear?
Yes, sir.
This condition is basically, it is without water. It is just like in isolated form. In isolated form, it is just Li plus. Is that clear?
Yes, sir.
So if it is only Li plus without water, without interacting with any other elements or compounds or anything, it will have lower mass, a smaller size. So it will move with more velocity.
Yes, sir.
So it will have higher ionic mobility.
Yes.
So always keep this in mind. If aqueous, it will reverse of without aqueous. Got it, Nara? If you have any doubt, Nara, you can ask me. Very good. What about this question? Can you do this?
Yes, sir. Just a minute.
This is aqueous, this is isolated.
So first one will be in descend. I mean increasing order, and the second one will be in.
Order of size is like this, right?
Yes, sir. Like that.
And the second one,
Increase. I mean it decreases, sir.
why? You want to see say this, right?
Yes, sir.
Why? See what happens here. The answer is very good. Okay. Li plus is here. It will be surrounded by water, right? It will be surrounded by water, yes or no?
Yes, sir.
This is Li plus, and it will be surrounded by water like this. And you know that this will be negatively charged, that it will be surrounding Li plus. So basically what happens here is there will be force of attraction between Li plus and water molecule, and water molecule from all sides will stretch lithium so much that it will larger than cesium in size. Is that clear?
Yes, sir.
It will be surrounded by a lot of water, and oxygen that has negative charge will stretch or attract lithium so much towards itself that it will stretch itself greater than cesium plus. That's why this happens. Okay,
Yes, sir.
just write it.
So we should say greater than sodium, right? Not cesium.
Greater than,
So we should say that it stretches more than sodium, right? So not cesium because.
it is greater than sodium, potassium, rubidium, cesium. I told you cesium because it is greater than all of this.
Okay, sir.
It covers all this. Okay.
Okay, sir.
Are you done with this?
Done, sir.
Melting and boiling point. Melting and boiling point. See, alkali metal, AM stand for alkali metal, has low melting point and boiling point because alkali metal has weak metallic bond. It has weak metallic bond due to its larger size. Due to larger size. Please write. Order of melting point or boiling point both in first group element, that is lithium, sodium, potassium, rubidium, cesium. You know that if bond length increases, bond strength will decrease or not.
Yes, sir.
So lithium has a smaller size. That's why lithium has a smaller size. It will have lesser bond length. That's why the lesser bond length, a stronger metallic bond will be there. So it will be in this order. Is that clear?
Yes,
A
sir.
stronger metallic. Are you done with this?
Done, sir.
Very good. Now see, there will be some other order or abrupt order, order of boiling point, order of boiling point in second. Second group, basically alkaline earth metal, beryllium, magnesium, calcium, strontium, and here it is barium. Now, what will be your expected order? Expected order is basically down the group it should decreases because size increases, metallic bond strength decreases. So the expected order is this. But what we found here, actual order, what is the correct order or actual order is basically beryllium will have most boiling point, followed by barium, then calcium, then strontium, and then magnesium. Why? Because group 2 element adopt or adopt different lattice structure. We will study about lattice structure in class 12 solid state. So basically this group 2 elements adopt different lattices, that's why its boiling point that's why basically its boiling point variations takes place. Okay.
Yes, sir.
Also, now we are going to compare between alkali metal and alkali earth metal, alkaline earth metal. So in note we can write alkali metal are generally soft, due to which or due to weak metallic bond. Due to weak metallic bond, it is soft. Second point we can write alkaline earth metal has higher melting point or boiling point or density than alkali metal because it has a smaller size. A smaller size means greater metallic bond or a stronger metallic bond, because alkaline earth metal has a stronger metallic bond than alkali metal. Is this clear?
Yes, sir.
Please write it and let me know if you are done with this. Are you done with this?
Yes, sir. Done.
Very good. Now going to talk about density. So I already wrote about this. Alkali metal has lower density. Alkali metal has low density due to larger size. You know that density has a formula, mass upon volume, right?
Yes, sir.
If size increases, volume increases, that means density decreases. And due to larger size, there will be weak metallic bond. Is this clear?
Yes, sir.
So basically, we can write order of density lithium, then potassium, then sodium. Sodium has more density than potassium because potassium is soft, more soft than sodium. Then rubidium, then cesium. or we can write basically potassium is lighter than sodium. Lighter than sodium. And you know that density has a formula, mass upon volume. If this decreases, density also increases. And you know that volume of potassium is greater than sodium, then density decreases. That's it. Is this clear? Done. Done. Are you done with this?
Just a second, sir.
Okay, okay.
Done, sir.
Very good. Now, beryllium, magnesium, calcium, strontium, then barium. What is the order of density? Basically, calcium has lower density than beryllium and magnesium, and then strontium, and then barium, and then radium you can write. And write a topic, flame coloration, which is very important. Same reason here.
Done, sir.
Then I'm going to write a point about flame coloration. Please write with me. Then I will explain. Alkali metal imparts characteristic color to the flame. This flame has energy. That's why. Due to which, or you can write due to low ionization energy, its valence electron gets excited so basically, alkali metal imparts characteristic color to the flame due to its low ionization energy. Its valence electron gets excited. During de-excitation, energy is released in terms of radiation, which lie in visible region. So what happens here is, just suppose the electron is here. One electron is here. This is the outermost cell electron. And when flame is nearby, this electron will get energy and it will excite and go to higher energy level. And then after some time, it will de-excite to its same energy level. During this excitation, it will release energy in the form of radiation, which lie in visible region, and we see color, flame coloration. Is that clear?
Yes, sir.
Now, which color we see? Basically, lithium shows crimson red, sodium shows yellow or golden yellow, rubidium shows violet color, Cesium shows blue color. Just write it.
Done, sir.
Very good. Now, what about alkaline earth metal? So basically, beryllium and magnesium do not show any flame coloration because its ionization energy is high. It doesn't get enough energy from flame to excite its electron. That's why it doesn't show any flame coloration. So write a point with me. In alkaline earth metal, beryllium and magnesium do not show flame coloration, and this is very important because beryllium and magnesium have higher ionization energy, due to which amount of energy required to excite the electron is not enough. Please write it.
Done, sir.
Done. Very good. Now write chemical properties. Chemical properties. Write with me. S block metals are highly reactive. In nature due to low ionization energy. Due to low ionization energy, size is larger and it can give its valence electron easily. That's why. Also, alkali metal is highly reactive because it has larger size and it can give its electron more easily than second group. Then alkaline earth metal, due to lower ionization energy or low ionization energy of alkali metal. Again, if you are going for order of reactivity, in the first group, lithium, followed by sodium, potassium, and then rubidium, and then cesium. And what about the second group? Beryllium, then magnesium is more reactive than calcium, then strontium, and then barium. When we compare between first and second group, first group will be more reactive than second group. Is that clear?
Yes, sir.
Please write it and let me know if you're finished with this.
Done, sir.
Now the second chemical property is about this. The reactivity towards hydrogen. You know, if the element M is from alkali metal and hydrogen, it has valency 1. And how it will react? MH. It will form MH, metal hydride. If this M dash is basically for alkaline or the metal, this has a valency 2, hydrogen has a 1, and it will form MH2. Is this clear?
Yes, sir.
This is from class 9th. You did it crisscross. So alkali metal reacts with hydrogen to form ionic hydride. To form ionic hydride, you can see metal and hydrogen will be found in H2 form. So it will be 2MH. You can balance it. Like lithium will react with hydrogen to form 2LiH, lithium hydride. In the same way, sodium also react with hydrogen to form 2NH. Is that clear?
Yes, sir.
And if you are going to talk about magnesium, magnesium will form MgH2. Are you done with this?
Done, sir.
Now we are going to talk about thermal stability. See, I'm going to make a chart which is applicable for everything about thermal stability in inorganic chemistry. How do we compare thermal stability? So thermal stability can be compared if the compound is covalent, then thermal stability is directly proportional to bond energy. If it is a there is a question in which you are going to arrange thermal stability, first check the compound is whether covalent or ionic. If compound is covalent, then go for its bond energy. The compound which has more bond energy will have more thermal stability. And if it is ionic compound, it will be divided into two parts. The first part is basically if the ionic compound is monoatomic anion. If there is monoatomic anion, since it is an ionic compound, it will have cation as well as anion if it is monoatomic anion, and if it is polyatomic anion. And what is mono and what is polyatomic anion? You know that mono, that means only one, like O minus 2 or N minus 3 or Cl minus or F minus, like this. And what about polyatomic anion? Polyatomic anion like SO4 minus 2, CO3 minus 2, NO3 minus, etc. Is that clear? If it has monoatomic anion, then thermal stability directly proportional to lattice energy. Thermal stability directly proportional to lattice energy. In that case, you are going to arrange it in lattice energy and then it is directly proportional. And in this case, polyatomic anion, thermal stability depends thermal stability depends on Fajan's rule that you have studied in chemical bonding. More covalent character, the compound which has more covalent character, less thermal stability. Less thermal stability. Is this clear?
Yes, sir.
So, did you make the chart?
Just a minute.
Okay, take your time.
Done,
you're
sir.
done with this, done, Krishna.
Yes, sir. Done.
Now we have thermal stability of hydride. What is the thermal stability of hydride? Thermal stability, that stands for basically a stability towards heat. A stability towards heat. So if you have given LiH, NaH, then KH, and then RBH, and then CSH. What I told you that is, if it is ionic or covalent, you know that it is ionic, it will depend upon basically LiH, NaH, KH. So basically it will depend upon its bond strength. TS depends on bond strength. So lesser size, a stronger bond. That's why the arrangement will be like this, order will be like this. Is that clear?
Yes, sir.
If
So
you have
one
any
thing,
doubt, you
sir,
can
but
ask
this
me.
is covalent, right?
Yes, you can say, or either, wait a minute, monoatomic. Thermal stability directly proportional to lattice energy. Lattice energy inversely proportional to size of ions. That's why the ions, size of ions.
Okay, sir.
So please write it, and then you can write all alkali metal hydride reacts with water to form metal hydroxide. So basically MH will react with H2O to give metal hydroxide plus H2O. If you are done with this, let me know.
Done, sir.
Now, another point about alkaline earth metal. So write with me, all alkaline earth metal except beryllium combine with dihydrogen upon heating to form their hydride. To form their hydride, like H2 will combine to form MH2. If you are going to heat it, like I wrote the equation, but it is possible only only when we heat it. BeH2 cannot be prepared with this method, so we prepare BeH2 in a special way. BeH2 can be prepared by the reaction of BeCl2 with lithium aluminum hydride, what LiAlH4, what it is called, lithium aluminum hydride. So how do we prepare? We take 2 moles of BeCl2 and react with LiAlH4. So it will give 2 moles of BeH2 along with byproduct LiCl and AlCl3. Please write it. Done.
Done, sir.
Your annual paper started, Krishna, or it's from 17th?
Sir, from 17th, sir.
Okay. Chemistry date?
Sir, it's on 27th.
Okay. Order of thermal stability, can you arrange this? BeH2, MgH2, BeH2, MgH2, CaH2, SrH2, and then BH2. This BeH2 and MgH2 has polymeric hydride. This will be in polymer form. That's why it will have more molecular weight, and if molecular weight increases, van der Waals force of attraction increases. That's why this will be like this. And these three are ionic hydride. These two are covalent hydride, and being covalent, its thermal stability is high because these two exist in polymeric hydride. That's why. Is that clear?
Yes, sir.
Please write it. And if you are going to react with water, it will form the hydride of second group element, metal hydroxide plus H2 will release, evolve. So I am going to write a reaction for calcium hydride. So it will form CaOH whole twice plus H2, 2H2.
Done, sir.
Very good. Now, the reactivity towards oxygen. Reactivity towards oxygen. So basically, there are three types of oxide. The first one is simple oxide, the second one is peroxide, and the third is superoxide. So normal oxide, we divided it into three parts. Normal oxide, in which oxygen has a charge -2. That it means it will take 2 electrons. Among alkali, only lithium forms normal oxide because it is very stable in this form. Li2. Sodium also form normal oxide, but it will prefer peroxide more. And then comes peroxide. Peroxide, that means O2 minus. That means there are two oxygen which has negative charge -2. One oxygen will have 1 electron. So among alkali metal, sodium forms peroxide. Sodium forms peroxide, that is Na2O. And the third is basically superoxide. So among alkali metals, potassium, rubidium, and cesium forms superoxide. that is MO2. Two electrons, sorry, two oxygen will require only one electron from one element from alkali metal because it can give only one electron. Is this clear?
Yes, sir.
No. Please write it.
So what is the formula for superoxide?
Superoxide, if you are going for potassium superoxide, it will be KO2. It will be RbO2. You know that one oxygen required two electrons. Whenever one oxygen takes two electrons, that is normal oxide. If one oxygen will take one electron and there will be two oxygen, that is basically peroxide. And if there is two oxygen and only one electron can give, potassium will only give one electron,
Yes,
so
sir.
it will share, that means superoxide. Is this clear?
Yes, sir. Done, sir.
Okay, just write it. Done.
Yes, sir. Done.
Very good. Now alkaline are the metal, and oxide, what type of oxide it will form? Write with me. Beryllium, normal oxide. It will form normal oxide. That means oxygen will take two electron, and we know that from second group element it can give two electrons easily, so it will be BeO. In the same way, magnesium also. What about calcium? Calcium form peroxide CaO2. CaO2. The oxide in which oxygen has only one oxidation state. One oxygen will take only one electron. Strontium, that is peroxide. This will also form peroxide. And barium, this will also form peroxide. So basically it will be SrO2 and this will be BaO. So peroxide generally in major group, in major amount, peroxide will be formed by hydrogen also. You know that hydrogen peroxide, sodium, and then calcium, and then strontium, and also barium. These all form peroxide easily. Done?
Done, sir.
Very good. Now we have reactivity towards air. Whenever we talk about air, that means we will react with oxygen as well as nitrogen. Reactivity with air. Air, that means O2 plus N2. So what happens here? I'm going to write with me. Among alkali metal, only lithium forms nitride. Only lithium forms nitride, that forms Li3N, due to lattice energy effect. And what does it mean? I will explain it. Lattice energy effect. It means a smaller size cation a smaller size cations forms a stronger bond with a smaller anion. Basically, lattice energy, why bond after bond formation or after forming a compound, the compound must have less energy so that it will be more stable. This is basically lattice energy effect. Lithium will have lower energy and nitrogen will have higher energy. When it will combine with each other, the energy will compensate, and that's why only lithium forms nitride, not with sodium, potassium, rubidium, cesium. Also, size matters. A smaller size cation react with a smaller size anion to form nitride. Sodium is larger. That's why sodium, potassium, rubidium, cesium does not form any nitride. Is that clear?
Yes, sir.
Are you done with this?
Just a minute.
So I'm going to write a list. Alkali metal. First, we are going to talk about oxide, major oxide, and then minor oxide. Are you done with the above one?
Yes, sir.
Oxide, we are talking about oxide. Just see, if I told you that only lithium forms oxide, it doesn't mean that sodium cannot form oxide. It will form, but in minor. The product will be in minor, because the product which is more stable, it will be in major form, and the product which is less stable will be in minor. That means lower quantity. Lithium only form oxide, Li2O. There will be no minor oxide. It will prefer to form major oxide as normal oxide. Okay. If I will write Li2O, can you read it as lithium oxide?
Yes, sir.
What about sodium? Sodium, the major product of major oxide is peroxide, but it can form oxide also, but it will be minor, lower in amount, because it is less stable in this as compared to this. Similarly, what about potassium? Potassium forms superoxide as major product, and potassium also form K2O2, that means peroxide, as well as it also form oxide, but in minor quantity. Rubidium, RbO2 in, cesium, CSO2. This will be in major quantity, and this will be in minor quantity. Okay.
Yes, sir.
But always remember this, except this lithium, this quantity, these elements do not react with nitrogen. So nitride, whenever you have a question, if sodium is reacting with air, what will be the product? The product will be only oxide, not nitride. Okay,
Yes, sir.
please write it. Done with this?
Done, sir.
Very good. This is alkaline earth metal. This is air. That means O2 plus N2. Going to write, if beryllium react, it will form beryllium oxide as well as Be3N2 nitride. If it will react magnesium with magnesium, it will form magnesium oxide as well as magnesium nitride. With the calcium oxide, it will form either calcium oxide or calcium peroxide, that is CaO2, plus with nitrogen, it will form Ca3N2. But this oxide is in minor, and this oxide will be major. What about strontium? Strontium is also will also form SrO2 slash SrO. This will be minor, but with nitrogen, it will form nitride. What about barium? Barium will also form oxide as well as peroxide, but this will be minor, and here it will form nitride. Done with this? Please write it and let me know if you are done with this.
Done, sir.
Very good. Now, write a note with me. Reaction of oxide with water. What it will form? Oxide, peroxide, and superoxide. If it is oxide, that is Li2O, and react with H2O, it will give hydroxide. And if it is peroxide, that means Na2O, will react with 2H2O to give sodium hydroxide along with peroxide, hydrogen peroxide. And what about superoxide? If it will react with H2O, it will give potassium hydroxide with O2 and H2O also. Please write it.
Done, sir.
Very good. Now, the next reactivity comes out to be reactivity towards halogen, right? Reactivity towards halogens. So, first of all, write a point which is very important. Fluoride, that means F minus of all S block element, and aluminum also. All S block, that means lithium, sodium, potassium, rubidium, cesium, beryllium, magnesium, calcium, strontium, barium, except are ionic in nature, except beryllium, BeF2. You know that all the second group element or first group elements, lithium, sodium, potassium, rubidium, cesium, or magnesium, calcium, strontium, barium, and aluminum, it all reacts with fluorine and it will form ionic compound. But with the beryllium, it will form covalent compound. Is that clear?
Yes, sir.
Now, the second point, which is very important, we talked about fluorine. Now, chlorine, Cl minus, chloride, bromide, and iodide of Na plus, Na plus, K plus, Rb plus, Cs plus. When these three react with this, are ionic in nature. Are ionic in nature. That means if lithium will react with chloride, bromide, or iodide, either one of them, it will be covalent in nature. Is that clear?
Yes, sir.
Now, Cl minus, Br minus, I minus of Li plus, comma, alkaline earth metal and aluminum have more covalent character due to Fajan's rule. According to Fajan's rule, we can also write. Are you done with this?
Done, sir.
Very good. Now, do you know what is Fajan's rule? Krishna?
Sir, I think it is like more charge, more covalent.
Yeah, always remember Fajan's rule. Size of cations inversely proportional to C plus. That means cations inversely proportional to polarization power. Polarization And if it is polarization power, that is PP directly proportional to covalent character. So if I'm going to talk about LiCl, NaCl, KCl, RbCl, CSCl, and I will ask which will have more covalent character, you have to see Li plus, all the anions are same. So Li plus is a smaller in size. If it is a smaller in size, high polarization power. If high polarization power, covalent character is more. The most covalent compound is this. We compare like this. Is that clear?
Yes, sir.
Now moving to the next part.
So just a second, sir. Can you scroll?
Okay.
Done, sir.
Wait a minute. Okay. Reaction with liquid ammonia. So whenever metal react with liquid ammonia, it will form two type of ion. M plus, it will, since it is metal, it will be cation. NH3 whole X plus, it loses electron, so it will be E minus, then NH3 whole one. Please write it, then I will explain.
Done, sir.
Very good. Now see basically what happens here. Just take its stoichiometric coefficient x plus y, so that NH3 is balanced. Here it will lose one electron, M plus, and NH3 will come to one of the metal and loses electron combined with NH3, another NH3, that is Y times. This electron is very important, and we can write the dilute solution. Write with me, the dilute solution of alkali metals and liquid ammonia produces ammoniated electron or cation. So ammoniated cation and ammoniated electron. This electron is known as ammoniated electron, and this cation is known as ammoniated cation. So basically this is ammoniated electron. So it reacts with this, like if we have sodium and react with 5NH3, it will be like this, NH plus and then NH3 whole twice plus electron will combine with NH3X. That means 3 or 2 you can take. Is this clear?
Yes, sir.
Another important about this is colored solution because of this ammoniated electron. So I'm going to write the dilute solution of alkali metal and liquid ammonia imparts blue color. Imparts blue color It is due to the presence of ammoniated electron. Since it is free electron, unpaired electron, so it is paramagnetic. So I'm going to write it is paramagnetic. Do you know what is paramagnetic and diamagnetic? Krishna?
No, sir.
Okay, no problem. Just write it and let me know. Done?
Done, sir.
Very good. So basically just write a point about paramagnetic and diamagnetic. Diamagnetic is one which has unpaired electron, If there is unpaired electron, that is paramagnetic is one which has unpaired electron, and diamagnetic is one which has no unpaired electron. That means all the electrons are paired. Is this clear?
Yes, sir.
Just write it and write a topic, the last topic, solubility of ionic compound. That is basically solubility of S block. We can also write. Please write a topic and then let me know if you are done with this.
Done, sir.
Very good. So basically solubility depends upon two factors. It depends upon two factors. The first factor is hydration enthalpy. We just defined it, what it hydration enthalpy. And the second one is lattice enthalpy. What is lattice enthalpy? The energy required or the enthalpy required to break 1 mole of solid into its gaseous constituent ions. That energy or enthalpy is called lattice enthalpy. Is that clear?
Yes, sir.
And hydration enthalpy, energy released or enthalpy released during the interaction of ions with water, that is called hydration enthalpy. Okay, so how do we compare? So basically, if lattice enthalpy greater than hydration enthalpy, if hydration enthalpy is lesser than lattice enthalpy, solubility decreases. Solubility of ionic compound decreases. Why it is so? Hydration enthalpy will be lower. That means the interaction between ions and water is very less. That's why it is decreases. The second point, if lattice enthalpy is lesser than hydration enthalpy, interaction will be more, bond will be formed, and it can be easily soluble. That means solubility of ionic compound increases. Is that clear?
Yes, sir.
Just write it.
Done, sir.
Done. Very good. Now, conclusion about solubility, which is very important to compare it. Generally, solubility, we are talking about generally, there will be exception also. Generally, solubility of ionic compound decreases from top to bottom. From top to bottom. It will decrease. And here is a star mark point. Solubility of carbonate. Solubility of carbonate of alkaline earth metal decreases. This means decreases from top to bottom. From top to bottom, because size of anion, since we are talking about carbonate, so size will be much larger. Size of anion being much larger than cation, lattice enthalpy, that's why lattice enthalpy will remain constant, within particular group, but hydration enthalpy decreases, enthalpy will decrease. If size of an ion are almost same, that means lattice enthalpy will be almost equal, remain almost constant, and hydration enthalpy will decrease if size of a cation will increase down the group. So the solubility of carbonate of alkaline earth metal decreases down the group. Is that clear? So if we are talking about carbonate BeCO3, MgCO3, CaCO3, SrCO3, DaCO3, down the group it will decrease. Simple. If we talk about generally in larger anions, I'm going to give you a list of larger anions. Larger anions is like, you already know that polyatomic anion, like CO3 minus 2 or HCO3 minus or NO3 minus or SO4 minus 2 or SO3 minus 2 or S2O3 minus 2 also, or I minus, we take it as larger anion, Br minus, these all are larger anions. And whenever larger anion is there, lattice enthalpy is almost same, and cation, due to cationic size, hydration enthalpy varies. If you are done with this, let me know, please. Done?
Just a minute.
Okay. Whenever larger anions, down the group decreases. Whenever a smaller anions, down the group increases. As simple as that.
Done, sir.
Very good. So can you arrange this? LiNO3 and then NaNO3 and then KNO3 and then RbNO3 and then cesium-NO3. In the same way, sulfate, we are going to talk about sulfate. So see, larger anions, so down the group it will decrease. So the solubility, order of solubility, what we are doing, order of solubility. Are you getting my point?
Yes, sir. Yes, sir.
So it will be like this, this, and this. Okay.
Yes,
Now,
sir.
when we talk about solubility of hydroxide of alkaline earth metal. What happens here? BeOH whole twice, MgOH whole twice, CaOH whole twice, SrOH whole twice, BaOH whole twice. These are all alkaline earth metal hydroxide. Basically, here the size is very less. Lattice enthalpy here increases, solubility decreases. Solubility decreases, and here lattice hydration enthalpy is more. That's why solubility increases like this. So basically, it's all about smaller anions. And what is smaller anions? Smaller anions like O minus 2, N minus 3, S minus 2, OH minus, F minus, Cl minus. When it comes down the group, it increases. Is that clear?
Yes, sir.
Please write it. So in general, I'm going to write a point which will be very important.
So when you're saying increasing and decreasing means it is increasing and decreasing across the group, right?
Yes, yes, across the group.
Done, sir.
Very good. Write a conclusion about this. Generally, anions are larger than cations, larger in size than cations. So, solubility decreases from top to bottom, from top to bottom. But in case of first A group, first group, that means alkali metal. In case of alkali metal, F minus 1, O minus 2, N minus 3. There is no N minus 3. We can write N minus 3 too. OH minus, CO3 minus 2. These all are exceptions, like HCO3 minus, SO4 minus 2, and SO3 minus 2. And also from second group, which means alkaline earth metal, that is F minus, O minus 2, or OH minus, solubility increases. Solubility increases from top to bottom, from top to bottom. So it is all summarized. If you have from first group, you are going to take it lithium hydrogen carbonate, NaHCO3, KHCO3. So from top to bottom, it will increase. Is that clear?
Yes, sir.
And in second group, with only this anion, it will increase. Otherwise, it will decrease. Just write it, then we will have some question.
Done, sir.
Generally, anions are larger in size, so solubility decreases from top to bottom. But in case of this, solubility increases from top to bottom. So if I'm going to take example that I already took, just suppose Li2CO3, Na2CO3. This is larger anion, and in larger anion, generally down the group, it decreases, right?
Yes, sir.
So it will basically here, in case here, it will increase. Is that clear? Solubility. Okay.
Yes, sir.
And in case of barium carbonate, magnesium carbonate, calcium carbonate, SrCO3, and barium carbonate, down the group, it decreases like this. And if you have BO, MgO, CaO, SRO, since O is present there, it will increase down the group. Okay.
Yes, sir.
BeO is almost insoluble, but BeSO4 is soluble in water. Why it is so? Please write this up to this and let me know if you are finished.
Done, sir.
Very good. So why it is so? BeO is insoluble and BeSO4 is soluble. It is because in BeO, lattice energy is high. If lattice energy is high, then it will be less soluble. Why its lattice energy is high? Because of a smaller size of cation and forms a stronger bond with a smaller anion. That's why. But when we talk about barium sulfate, beryllium sulfate, less lattice energy, more hydration enthalpy. So that's why. Okay.
Yes, sir.
So here the chapters completed. Do you have any doubt? Okay, so please write it and then I will tell you some important points regarding S block, which is very important. Are you done with this?
Just a minute.
Okay, take your time.
Done, sir.
Okay. Lithium and magnesium shows diagonal relationship. Basically, some of the properties of lithium and magnesium are similar, and they are known as the diagonal relationship because lithium is here and magnesium is here. So it will be like this. So it is known as diagonal relationship. Why they are called diagonal relationship? What is similarity basically? So lithium and magnesium are harder in their group. Also, lithium and magnesium react with cold water, reacts with cold water. Third is Li2CO3 and MgCO3. When we heat, it will give metal oxide plus carbon dioxide, and LiCl and MgCl2 are deliquescent. What is deliquescent? Do you know? Deliquescent, that means absorb moisture. The compound which absorb moisture, that is basically deliquescent. So LiCl absorb moisture and it exists in this form. MgCl2 do the same, but it has greater hydration enthalpy, so it will have 8H2. In NCERT, there will be similarity and dissimilarity. So please read that paragraph, it is very important. In S block, similarities between lithium and magnesium and dissimilarity.
Done, sir.
Done. So the chapter is complete here. Do you have any doubt?
No, sir.